environment with obstacles, finding shortest paths. You know who uses this right now a lot? Amazon. Amazon has these warehouse robots. These huge warehouses. I mean, look at how much they've done. Basically, you put an order, they'll keep on telling you, okay, your sock has been now put into the packet. Now the packet is out the door. Now the packet is in the truck. Now the truck guy is coming up. All this stuff they're able to track. So one of the things they do in the warehouses essentially is these little robots that were made by this guy called Kiva company. Essentially just find their paths to get to the human workers who will put stuff into the packets. Humans have been now reduced to putting stuff into the packets. After a while, that will also be gone, and so Amazon will be automated. Okay? But these paths, these multi-agent paths, are being made by these kinds of algorithms. Actually, a more general algorithm called MapF sorts of problems where multiple robots with multiple goals have to get to those goals in the fastest way possible without bumping into each other, and also not bumping into people. And of course, also not bumping into obstacles. It's a great example. Okay? So you have search algorithms, and again, ultimately, search algorithms are extremely simple to understand. You start, you have been basically you have a queue of nodes. Initially, you put the initial state as the node, and then you pick a node from the queue, you apply the child generator function, you get new nodes. In fact, before you apply the child generator function, when you pick the node from the queue, you ask the goal test function, is this a goal? If it's a goal, you stop. If not, then you call the child generator function. It will generate more children who are then made into search nodes and put into the queue. One interesting thing that people should remember when they first start doing search is you only ask the goal test function, is it a goal, when you pick the node from the queue. When you find that that node is not a goal node, you expand it, and one of the children is a goal node, you don't stop them. If you stop them, many properties are lost. All the properties that we prove for search algorithms basically say that when you pick a node and when you pick a node for expansion, and you find that it is a goal node, will you be optimal? Okay? Now let's play I'll move over this, and let's play some Socrates. Okay. So the first question. Already people are answering. Apparently we have lost.
Let's save your time.
Yeah.
What?
Oh, yeah.
First for search and worst case, good point. Time complexity. Good point. Time point. Did you not get this? Okay, I didn't. No, I think people are answering, so I assume it's working. Is this working for people? Okay, so I can show you what's happening here. Okay, so the question is depth first search and depth first search both have the same worst case complexity. True. Because they're basically, in the worst case, both of them have to do the full tree. And if you look for a uniform tree with a depth d, then they are b power d, order of b power d rows. They have to look at all of them. They have to expand all of them. The cost is expanding the nodes. Yes? No, I'm talking about uniform search tree model. Okay, the node looping is a different problem. So assuming that, in fact, yeah, so if there is loops, then depth first search can get into trouble. Okay, the second one is if the agent is feeling lucky, okay, I should show you that again. And then I'll just finish this. Just this or something. Finish. And one more thing for question. Okay, and let me show you this. If the agent is feeling lucky, it should use breadth first search. True or false? The fun part is you know these two search algorithms. You have learned about them in 310. I'm just asking you to take a fresh look. If you are feeling lucky, should you use breadth first or depth first? Okay? So what are people saying? Apparently, you should use depth first because breadth first essentially will go level by level by level by level by level. If you are lucky, you should do depth first because it might go directly to the goal. So that's the interesting difference between depth first and breadth first. The worst case for both are the same. And what's interesting, even the average case for both are pretty much the same. That's actually an interesting proof, but average case is also the same, more or less. The real difference is if you are one of these people who think that gods have favored them, then you should do depth first. Okay? The next one is, so then I'll just finish this. Another true false. Depth limited depth first search is complete and optimal. Okay, sorry. Depth limited depth first search is complete and optimal. Complete, again I'm assuming you read the textbook, okay? Complete, put on brackets. Complete means if there is a solution, you will find a solution. Optimal means if there is a solution, I'm sorry, in fact, more importantly, complete means if there is a solution, you will either find the solution or terminate. Optimal means if there is a solution, you will find the optimal solution, the shortest cost solution. Let's see what people say. So most people said false, but unfortunately there is a conjunction, so they don't know what the heck they're saying false for. So here's the answer. For the depth limited depth first search, if there is a goal within the limit, then you have a finite tree, so you should be able to find, you should be able to exhaust, and you should be able to find the solution if there is a solution. However, even if there is a goal in your depth limit, you may still, there may be more than one goal in your depth limit. And you might find the deeper goal, just based on your luck. And really, and I'll stop here, what iterative deepening depth first search is doing is using this property. What it's saying essentially is, since depth limited depth first search is complete, but not optimal, and I put depth limit to be 0 first, then 1, then 2, then 3, then 4, and keep doing depth limited searches, then the first goal you find, let's say, is in the level 10, which means there was no goal until level 9. There may be more than one goal in level 10, but they are all equally good. That's how I try to do depth first search is optimal. We'll stop here.